The initial part of my career was helicopters, trained by a company called Bristow Helicopters, went to the North Sea, did 7 or 8 years up there, flying out to the oil rigs, oil platforms, and then moved from there into fixed wing and a series of airlines, which culminated in flying for British Airways for the last 37 years flying.
How does a helicopter actually stay in the air? I mean, think about it. These machines lift straight off the ground, hover like they're hanging on invisible strings, and glide in any direction they want. No runway, no wings, just spinning blades and some serious engineering magic. But here's the thing, what you think you know about helicopters? Yeah, it barely scratches the surface. Because behind every smooth takeoff is a story of centuries-old dreams, brilliant inventions, and materials so advanced they could belong in a sci-fi movie. From wooden blades handcrafted like fine furniture, to cutting-edge composites that think before they break. And no, it's not just about spinning fast and hoping for the best. Today we are pulling back the curtain to show you how helicopters are really made. The secrets behind the rotors, the battles against gravity, physics, and even Mother Nature herself. And how these flying marvels evolved from clunky prototypes to life-saving machines and soon maybe even self-flying taxis. So buckle up, because this isn't just another How It Works video. This is the story of how humans conquered vertical flight and where we're heading next. Let's get into it. The ancient dream of vertical flight. Once you have tasted flight, you will forever walk the earth with your eyes turned skyward. Attributed to Leonardo da Vinci. Long before engines, rotors, or even the idea of airplanes, humans were already dreaming of flying. Not just forward, but upwards. Believe it or not, the first known helicopter was a toy. Around 400 BC, kids in China were playing with simple bamboo spinners. You'd twist the stick between your hands, let go, and watch the little rotor fly into the air. It wasn't exactly high-tech, but the idea was there, using spinning blades to lift off. Fast forward to the 1480s, and none other than Leonardo da Vinci sketched out a curious machine called the aerial screw. Picture a giant spinning screw made of linen and wire, designed to twist its way into the sky. It never flew, but Leonardo's concept was the seed of something big. The belief that vertical flight was possible. For centuries, though, that dream stayed grounded. The problem wasn't imagination, it was technology. No one had engines light or powerful enough to lift a person straight into the air. That changed in the early 1900s when inventors started experimenting with real, manned flying machines. In 1907, French engineer Paul Cornu built what many consider the world's first helicopter to lift off with a person on board. It wasn't exactly graceful, it hovered just a few feet off the ground and needed people to hold it steady. But history had been made. Then came another French pioneer, Etienne Emichan, who took things further in the 1920s. He added stabilizing rotors and, in 1924, managed to fly over 1 kilometer, a huge leap forward. Still, these early machines were tricky, unreliable, and frankly dangerous. But the idea had taken flight, literally. The world was on the edge of a breakthrough. So who finally cracked the code and built a helicopter that wasn't just experimental, but practical? That's where Germany steps into the spotlight. First flights, from wobbly prototypes to practical machines. The helicopter is evidence that with enough engineering, even the impossible becomes routine. Aviation historian. By the 1930s, engineers were racing to turn those awkward flying contraptions into real, reliable aircraft. The winner? A German design that would change aviation forever. In 1936, the Focke-Wulf FW-61 took to the skies. Unlike its predecessors, this wasn't just a machine that could hover for a few seconds. It could actually fly, control its movement, and land safely. For the first time, the world saw what a practical helicopter looked like. The secret sauce? Twin rotors mounted on either side of the fuselage, spinning in opposite directions. This clever design canceled out the twisting force that plagued earlier helicopters. No more spinning out of control. The FW-61 was stable, maneuverable, and surprisingly capable for its time. But the real breakthrough came a few years later, across the ocean. In 1942, aviation pioneer Igor Sikorsky unveiled the VS-300, the first helicopter to enter full-scale production. Sikorsky's design introduced something we still see today, a single main rotor with a tail rotor to handle stability. Simple, elegant, and effective. Suddenly, helicopters weren't just experimental toys for engineers. They were tools. The military quickly saw their potential for reconnaissance, transport, and rescue missions. Civilians followed, using them for everything from medical evacuations to news reporting. And here's a cool fact. The Sikorsky Company still makes helicopters today, nearly a century later. From bamboo toys to battlefield workhorses, the helicopter had finally earned its place in the skies. But building one? That's a whole different story. Because once you know how a helicopter flies, the next question is, what are these things actually made of? Stay tuned, because in the next part, we'll head straight to the factory floor and discover why every gram of material matters when you're building a machine that defies gravity. Building a bird, the art and science of helicopter materials. In aviation, weight is the enemy. Every pound saved is a mile gained. Aerospace engineers saying, when you look at a helicopter, you probably notice the spinning blades, the cockpit, maybe the tail rotor. What you don't see is the intense thought that goes into what it's made of. Because here's the thing, every kilogram matters. If it's too heavy, it simply won't fly. That's why helicopter manufacturing is a careful game of balance. Engineers are constantly asking, how do we make this strong enough to survive harsh conditions, but light enough to get off the ground? The answer? A mix of metals and composite materials. Now, composites might sound fancy, but they're basically materials made by combining two or more things to get the best of both worlds. Lightweight, but tough. Think fiberglass or carbon fiber. These materials are superheroes when it comes to saving weight without sacrificing strength. In fact, in military helicopters, composites can make up 80% of the fuselage. When missions depend on speed, agility, and fuel efficiency, every bit of weight savings counts. But it's not all high-tech fibers. Metal still plays a leading role, especially when it comes to parts that need to handle serious stress, like the engine mounts or rotor hubs. Metals like aluminum and titanium offer reliability that composites sometimes can't match, especially when cost is a factor. Speaking of cost, this is where things get tricky for civilian helicopters. While the military can afford cutting-edge materials, commercial manufacturers often have to watch their budgets. Plus, strict FAA regulations make working with composites more expensive, thanks to detailed testing and certification processes. So depending on who's building the helicopter and what it's used for, you'll see a different recipe of materials. Some companies go all in on composites, while others stick with metal where they can. At the end of the day, whether it's flying over battlefields or city traffic, a helicopter is a masterpiece of material science. But if there's one part where material choice really tells a story, it's in the blades. Next, let's rewind to a time when rotor blades weren't made in high-tech factories, but in workshops that smelled more like sawdust than jet fuel, when rotor blades were made of wood. If it flies, floats, or drives, someone probably built it out of wood first. Old engineering joke. Believe it or not, the first helicopter rotor blades had more in common with a handcrafted canoe than a modern aircraft. Back in the early days of aviation, wood was the go-to material. Why? Because it was light, flexible, and surprisingly strong when handled right. Plus, it was easy to shape if you had the patience and the carpentry skills. Those early rotor blades were a work of art. Built from layers of spruce, birch, and balsa wood, each blade was carefully glued, sanded, and balanced by hand. They were then wrapped in fiberglass and sealed with aircraft paint to keep out moisture. But here's the catch. Wood doesn't like the weather. Rain, humidity, and even temperature changes could weaken the blades over time. And since blades always fly in pairs, if one got damaged, the other was useless too. Even though they were called infinite life blades, early wooden rotors had a bad habit of soaking up water or cracking under stress. Pilots and engineers quickly realized that while wood was a great start, it wasn't the future. To protect these delicate blades, manufacturers added metal leading edges, thin strips of stainless steel to handle wear and tear. This idea of combining materials, wood, fiberglass, and metal, was the first step toward the composite structures we see today. But eventually, the industry needed something tougher. Something that wouldn't warp in the rain or need replacing every time a bird sneezed on it. That's when metal blades took over. Stronger, more durable, and easier to maintain, or so they thought. Because while metal solved one problem, it introduced another. one that could turn a small crack into a big disaster. Let's find out how the switch to metal changed everything, for better and worse. The metal age, stronger, but with a catch. Metal remembers its mistakes, it cracks where it's weakest. Aviation maintenance proverb. Switching from wood to metal rotor blades felt like a no-brainer at first. After all, metal's tough, weather-resistant, and doesn't mind a bit of rough handling. Finally, engineers had a blade that didn't flinch at a rainstorm or warp in the summer heat. But as with most things in aviation, solving one problem often reveals another. While metal blades were stronger, they came with a hidden weakness: fatigue. Over time, tiny cracks could form in stressed areas, and unlike wooden blades that might give you a visual clue or gradual performance drop, metal blades could fail suddenly and catastrophically. There were no second chances. If a crack went unnoticed, it could grow fast, tearing through the blade like a zipper. That's why metal blades were given strict design lifespans. After a certain number of flight hours, they had to be replaced, whether they looked fine or not. To boost strength without piling on weight, engineers got creative. They introduced honeycomb structures, lightweight cores sandwiched between metal skins. This added stiffness and durability while keeping blades light enough for flight. But even with these improvements, metal still had its limits. The manufacturing processes of the time made it hard to design anything beyond simple shapes. And the risk of sudden failure was always in the back of every pilot's mind. The industry needed a blade that was smart enough to fail safely, something that would warn you before things went wrong. Enter the Composite Revolution. In the next chapter, we'll see how materials like fiberglass didn't just improve blades, they changed the rules of helicopter safety forever. The Composite Revolution. Smarter, safer, stronger. It's not about being unbreakable, it's about knowing when something's about to break. Helicopter design engineer. By the time engineers had pushed metal blades as far as they could go, it was clear strength alone wasn't enough. What helicopters needed was a blade that could warn you before things went wrong. That's where composite materials changed the game. When fiberglass, foam cores, and honeycomb structures entered the scene, rotor blade design took a massive leap forward. These weren't just lighter than metal, they behaved differently under stress. Instead of snapping without notice, composite blades showed signs of damage, like small cracks or vibrations, giving pilots precious time to react. Think of it like this. Metal blades are like glass, strong but brittle. When they fail fast. Composite blades, on the other hand, are like fabric. They might fray, but they won't just tear apart instantly. This non-catastrophic failure mode was a lifesaver, literally, and composites offered another bonus: design freedom. Unlike metal, which was hard to shape, composites could be molded into complex aerodynamic forms. Engineers started experimenting with curved blades, asymmetrical profiles, and custom tips that boosted performance and reduced noise. Suddenly, rotor blades weren't limited to simple straight shapes anymore. Designers could fine-tune them for speed, efficiency, and safety all at once. Of course, nothing's perfect. Composites were more expensive to produce, and repairs required specialized knowledge. But when it came to saving lives and pushing performance, it was a price worth paying. With these new materials, helicopters weren't just safer, they were faster, smoother, and more capable than ever before. Speaking of speed, the next big challenge wasn't just staying in the air, it was seeing how fast a helicopter could really go. And that's where blade design went from clever to revolutionary. Racing the wind, how blade design broke speed records. To fly fast in a helicopter, you don't just need power, you need to outsmart the air. Test pilot, British Experimental Rotor Program. If you've ever wondered why helicopters don't zoom through the sky like jets, here's the secret. It's not about the engine, it's about the blades. As a helicopter speeds up, something strange happens. The blade spinning forward cuts through the air faster, generating more lift. But the blade swinging backward? It slows down, creating less lift. At high speeds, this imbalance becomes dangerous. The backward blade can stall, causing violent shaking, or worse, loss of control. This problem set a natural speed limit for helicopters, until a group of British engineers decided to rewrite the rules. Enter the British Experimental Rotor Program, BERP, in the 1980s. Their mission? Build a rotor blade that could handle high speeds without falling victim to physics. The solution was genius. They swept back the tips of both the leading and trailing edges of the blade. This design reduced air resistance at extreme speeds and delayed the dreaded stall on the backward blade. In August 1986, their work paid off. A modified Westland Lynx helicopter, equipped with these revolutionary blades, hit a jaw-dropping 249 miles per hour, a world record that still stands today. But speed wasn't the only benefit. The swept-tip blades also made helicopters more stable and efficient at normal speeds, reducing noise and vibration. Of course, chasing speed comes with trade-offs. The advanced blade shapes added a bit of extra weight, and the designs were complex to manufacture. But the performance gains were undeniable. Thanks to innovations like burp, modern helicopters can fly faster, safer, and smoother than ever before, without crossing that invisible line where aerodynamics turn dangerous. So next time you see a helicopter slicing through the sky, remember it's not just about raw power. It's about clever engineering, smart materials, and blades designed to outthink the wind. But even with all these advancements, helicopters still have limits. Push them too hard and nature fights back. In the next part, we'll explore what happens when things go wrong, and how pilots and engineers work together to keep these machines dancing safely in the sky. Dancing on air, flight dynamics, and saving lives in the sky. Flying a helicopter is like patting your head, rubbing your belly, and tapping your foot while balancing on a tightrope. Helicopter flight instructor. By now, it's clear helicopters are engineering wonders, but even with smart materials and clever blade designs, they still have to obey the laws of physics, and sometimes those laws can be unforgiving. One of the biggest challenges in helicopter flight is managing blade stall, especially during high-speed forward flight. Here's how it works. As the main rotor spins, one blade moves forward into the wind, while the other swings backward. The forward blade slices through the air faster, creating more lift. But the backward blade, it slows down relative to the airflow and starts losing lift. At low speeds, this isn't a problem, but push a helicopter too fast and that backward blade can stall, just like when an airplane wing stops generating lift. When this happens, the rotor becomes unstable. The helicopter starts shaking violently, and worse, it might roll to one side, usually toward the stalled blade. For a pilot, this is a heart-pounding moment. The helicopter might suddenly lurch upward or sideways, forcing them to react quickly. So what's the fix? Modern helicopters are designed to warn the pilot before things get out of hand. Subtle vibrations signal that they're reaching the danger zone. The correct response? Stay calm, reduce speed, lower the blade angle, and let the rotor spin faster to regain stability. But here's where advanced blade design, like those swept tips we talked about, really shines. They help delay stall and give pilots more breathing room. Still, every helicopter has a speed limit, determined by weight, blade design, and air conditions. No amount of technology can fully erase that boundary, at least not yet. This delicate balance between lift, speed, and control is why helicopter pilots are some of the most skilled aviators out there. They're constantly adjusting controls, reading the machine's subtle signals, and staying one step ahead of physics. So next time you see a helicopter gliding smoothly through the air, remember, behind that calm flight is a dance with invisible forces and a pilot making sure every move stays in harmony. But what if we could push those limits even further? What if the future of helicopters wasn't just about managing risks, but eliminating them entirely? Let's take a glimpse at where rotorcraft innovation is heading next. The future of helicopters, where innovation takes flight. The helicopters of tomorrow won't just fly, they'll think, adapt, and maybe even fly themselves. Aerospace futurist. Helicopters have come a long way from bamboo toys and wooden blades. But if you think today's rotorcraft are impressive, just wait, because the future of helicopter technology is set to redefine what these machines can do. First up, there's a major shift toward electric and hybrid helicopters. Companies around the world are racing to build quieter, cleaner rotorcraft that can zip across cities without burning a drop of fuel. These are the so-called air taxis you've probably heard about, designed to beat traffic by taking commuters to the skies. And it's not just about going green. Electric motors allow for simpler designs, fewer moving parts, and reduced maintenance costs. Imagine a helicopter that's easier to fly, cheaper to run, and silent enough to operate in busy urban areas. Then there's autonomous flight. Thanks to advances in AI and sensors, Future helicopters might not need pilots at all, just a destination. Self-flying rotorcraft are already being tested for cargo deliveries and search and rescue missions in dangerous areas where human pilots would be at risk. On the materials front, research continues into next-gen composites, even lighter, stronger, and smarter materials that can self-detect damage or adapt their shape mid-flight to improve performance. And for those who crave speed, new designs like compound helicopters and tilt rotors combine the best of helicopters and airplanes. These hybrids can take off vertically, but switch to airplane mode for fast, efficient cruising, breaking past traditional speed limits. Of course, challenges remain. Regulations, safety concerns, and infrastructure need to catch up with these futuristic ideas. But the direction is clear. Helicopters are evolving from mechanical wonders into intelligent, versatile flying systems. So as we wrap up this journey through the world of rotorcraft, one thing's certain: the story of helicopters is far from over. From ancient dreams to cutting-edge designs, helicopters have always been about pushing boundaries. And in the skies of tomorrow, they'll fly higher, faster, and smarter than ever before. If you enjoyed this deep dive into how helicopters are really made, let us know in the comments. What surprised you the most? Don't forget to like, share, and subscribe for more behind-the-scenes looks at the machines that shape our world. See you in the next one, where innovation takes flight.